Welcome to the Deep Dive. Today we're looking at exoplanets, specifically how the Gaia Space Observatory is really changing the game.
Yeah, it's kind of a quiet revolution happening in the background of all those discovery headlines.
Exactly. We're trying to cut through the noise.
Yeah.
Based on the latest research, we want to figure out how Gaia is pushing things forward, not just finding more planets, but really understanding them.
Right. So our mission, let's say, is to see how Gaia helps confirm these planets and pin down their properties, especially how it works with data from, say, Kepler and TESS, and even direct imaging.
And this isn't just us thinking this is important. The 2022 Sagan Summer Workshop at Caltech, it was all about exoplanet science in the Gaia era.
Named for Carl Sagan, of course. Always worth remembering his impact.
Absolutely. Son of a Ukrainian refugee,
Yeah.
testified about climate change way back in '85.
Yeah.
Quite the visionary. Anyway, the workshop, organized by Alessandro Sozzetti and Jackie Faraday, had people like Anthony Brown, Orla Creevy, Sozzetti himself,
Mm.
all talking about Gaia's huge role.
It shows you the whole community is realizing, okay, Gaia isn't just a tool, it's becoming the tool for getting the details right. A real shift.
Okay, so let's break it down. We'll focus on three main things Gaia's doing. First, sorting out those transit candidates, figuring out which ones are real.
Hmm.
Second, making sense of radial velocity data, getting the true mass.
Yeah, that's a big one.
And third, how it's helping out with the really tricky business of directly imaging planets.
Sounds like a plan. Let's start with the transits. Missions like Kepler and now TESS, they find potential planets by looking for that tiny dip in starlight when something passes in front.
Right, and they've found loads.
Hmm.
The NASA Exoplanet Archive shows
Yeah.
Kepler confirmed, 2711 planets? But it still has over 2,000 candidates waiting.
And TESS is even more dramatic. Something like 233 confirmed, but nearly 6,000 candidates.
Whoa.
Yeah, that huge difference really tells the story. Just seeing a star dim periodically isn't proof of a planet. There are imposters, false positives.
Well, what kind of thing?
Well, you could have a binary star system where one star just grazes the edge of the other, causing a small dip. Or maybe there's an eclipsing binary star pair way off in the background, but its light blends with your target star, and that combined light dips. Looks like a transit, but isn't.
Ah, okay. And that's where Gaia comes in, because it sees things more clearly.
Exactly. See, Kepler's pixels were pretty big, relatively speaking, 4 by 4 arcseconds. Think of it like slightly fuzzy vision. You could easily have more than one star crammed into that single pixel, an unresolved binary or that background eclipsing binary.
And you wouldn't know it. So you might think it's a planet transit, or you'd get the planet size totally wrong if it was real, but diluted by other starlight.
Precisely. But Gaia, its vision is incredibly sharp. It can tell two stars apart even if they're only separated by zero point 0.7 arcseconds. Much, much finer detail.
So it can spot those hidden background binaries or nearby stellar pairs that were fooling Kepler.
It certainly helps weed a lot of them out. Plus, there's this thing in Gaia's Data Release 3 called RUWE. It's like a measure of, well, astrometric noise. Basically, how smoothly the star appears to move.
Okay.
If the star's path is a bit wobbly or noisy, a high RUWE value, it could be a sign that there's an unseen companion tugging on it. Maybe another star, not necessarily a planet causing a transit. So that's another flag Gaia provides.
And this must be even more important for TESS, right? You said its pixels are way bigger.
Oh, much bigger, 21 by 21 arcseconds. So the chances of blending, of background contamination are significantly higher. Gaia's ability to resolve those crowded fields is absolutely crucial for vetting the test candidates.
Okay, that makes sense. So Gaia acts like a high-resolution filter for transit surveys.
That's a good way to put it. Now let's talk about radial velocity, the other main planet-finding technique. Detecting the star's wobble caused by a planet's gravity.
Right, the Doppler shift method. But the problem there, as I understand it, is you only see the motion towards or away from us along the line of sight.
Exactly. So when you calculate the planet's mass from that wobble, you only get a minimum mass because you don't know the tilt of the orbit, the inclination, the sin factor.
Yeah, like seeing someone lift weights only from the side, you know they're lifting something, but not exactly how much, unless you see the full motion.
Perfect analogy. But Gaia measures the star's position in 2D on the plane of the sky. It tracks that tiny side-to-side wobble over years. Combine that with the radial velocity.
Yeah, and you can figure out the actual 3D motion, the inclination, and nail down the true mass.
That's the key. And this has led to some pretty dramatic reevaluations. Take HD 92987b.
Okay.
Radial velocity suggested a minimum mass around 17 Jupiters. Pretty hefty. Orbiting far out, too. People were thinking, hey, maybe we can directly image this thing.
Sounds promising.
But then Gaia measured its astrometric signal, that side-to-side motion, and the wobble was, well, huge, much bigger than expected for a 17 Jupiter mass object.
So what was it?
Turns out the companion wasn't 17 Jupiters, it was more like a quarter the mass of our sun, a small star. And the orbit was almost edge onto us, nearly polar, like 175 degrees inclination.
Whoa. So not a planet at all, but a star in a weird orbit.
Exactly. Gaia completely changed the picture for that system.
Amazing. What about other examples?
Well, there's HD 1014762b. This one's famous, sort of, found way back in 1989. Minimum mass, about 11 Jupiters. They called it a probable brown dwarf even then. Very cautious.
One of the very first hints of planets outside the solar system, right?
Indeed. And Gaia looked at its star's motion. It found what's called excess astrometric noise, that slight extra jiggle we mentioned earlier.
Like their RUWE thing.
Similar idea, yeah.
Yeah.
That extra noise supported the idea it wasn't just an 11 Jupiter mass object. Gaia's data pointed to a very low inclination, only about 6 degrees. Tilted way over from our perspective.
Meaning the real mass must be
Much higher, around 100 Jupiter masses. So firmly in the brown dwarf category, too big for a planet, too small to be a star. Gaia basically confirmed the original suspicion after decades.
So it's not just finding planets, it's clarifying what these things are. Planets, brown dwarfs, small stars.
Precisely. It helps us sort out the categories. Which brings us nicely to the third area. Direct imaging. Actually seeing the planets.
Which sounds simple, but is incredibly hard. Trying to see a faint planet right next to its incredibly bright star.
It's like spotting that firefly next to a searchlight. Yeah. A huge technical challenge.
But why bother? What's the payoff?
Oh, huge payoffs. You directly confirm the planet exists. You can find planets on really wide orbits that take centuries to go around things RV and transits might miss. You can actually track their orbits over time.
See them move.
Yep. Jason Wang has made these amazing time-lapse movies of systems like Beta Pictoris, HR 8799, Fomalhaut. You see the planets physically moving. Plus, you can study their atmospheres with spectroscopy, maybe even image surfaces someday, way down the line.
Okay, so super valuable, but super hard. We only have, what, maybe 60 systems imaged so far?
Around that number, yes. It's growing, though. And Gaia is helping here, too, in a really interesting way, leveraging time. Time. How?
Well, remember, Gaia isn't the first super precise space astrometry mission. There was Hipparcos back in the early 90s.
Ah, right.
So now we have this time baseline between Hipparcos and Gaia, nearly 30 years of high-precision measurements of where stars are and how they're moving.
Okay, and how does that help find planets?
Think about a star with a really massive planet on a very wide, long-period orbit. Maybe takes hundreds of years to go around. Over just a few years, the star's path through space looks like a straight line.
Makes sense.
But over decades, that slow, steady gravitational tug from the distant planet will cause a tiny, tiny change in the star's velocity, a slight curve in its path, an acceleration.
So Hipparcos measured its position and motion then. Gaia measures it now, and if the motion isn't perfectly constant...
You've detected an accelerating system. That acceleration is a big clue that there's a massive, long-period companion pulling on the star. Maybe a giant planet or a brown dwarf.
And you can spot this even if you can't see the companion directly? Exactly. It tells you something massive is out there. And these accelerating systems become prime targets for direct imaging campaigns, like HD 33632.
Tell me about that one.
Okay, so direct imaging found a faint companion orbiting this star, pretty far out. But then astronomers looked at the Hipparcos Gaia data. They found this tiny acceleration signal, just 10.5 milliarcseconds over those decades.
Tiny.
But measurable. And from that acceleration, they could calculate the companion's mass dynamically. Turns out it's about 46 times the mass of Jupiter, a brown dwarf, most likely. Gaia helped pin down its mass just from the star's motion.
That's incredible, using data decades apart to weigh an unseen object.
It is pretty cool. And it's not just HD 33632. Other accelerating systems have been flagged around stars like Pi Mensae, HD 984, HIP 21152. There have been surveys finding dozens of these candidates.
So this Hipparcos Gaia acceleration technique is basically pointing the direct imaging telescopes where to look.
It's a powerful synergy, yes. It identifies systems where massive, distant companions are likely lurking, making those tough imaging searches much more efficient. And there's huge potential for finding many more as imaging gets better and we get more Gaia data.
Okay, wow. So let's try and wrap this up. Gaia is really doing a lot more than just mapping stars.
Oh, absolutely.
We've seen three big ways it's impacting exoplanet science. First, It's cleaning up the transit candidates from Kepler and TESS, getting rid of false positives. Essential quality control.
Vital.
Second, it's giving us the true mass for radial velocity planets by measuring that crucial orbital tilt, turning minimum masses into actual masses.
Right, adding that third dimension.
And third, by using that long-time baseline with Hipparcos, it's finding these accelerating stars, pointing us towards massive distant companions, perfect for direct imaging follow-up.
Exactly. It's like Gaia provides this fundamental layer of context and precision that benefits all the other techniques. It cross-references, validates, it helps build a much more solid, reliable picture of these planetary systems.
It really feels like a cornerstone mission now for exoplanets.
I think that's fair to say. Yeah.
So, looking ahead, as Gaia keeps collecting data, releasing more precise measurements, what does that mean? How might this change our view of planets in the galaxy?
Well, that's the exciting part, isn't it? We get a more accurate census. Maybe we'll find that certain types of planets are more or less common than we thought. Maybe its precision will finally let us detect the wobble from truly Earth-mass planets around nearby stars.
Or maybe find completely unexpected systems, things that don't fit our current models of how planets form.
That's always a possibility in astronomy. Gaia is giving us such an unprecedented, detailed look at stellar motions. Who knows what subtle signals might be hiding in that data, pointing to things we haven't even conceived of yet. It really makes you wonder what surprises are still out there.